Hello, everyone. Welcome to the next part of the lecture. In this part of the lecture, we are going to do the transfer function and a circuit problem. Transfer functions are very important. We're going to kind of define what a transfer function is, why it is useful, and then we're going to do an example problem. And they're very useful because I'm going to kind of, after at the end of this chapter, we're going to carry over these concepts to design filters. A very important concept. Okay, so let's get started. So transfer function in the S domain is essentially a ratio of an output to the input, right? An output and input can be anything. So for example, you could have a circuit where your input is input voltage source. Maybe you have like multiple sources. That input can be any one of them. And your output could be a particular voltage across a resistor, a particular voltage across an inductor, across a capacitor. So input and output can potentially be defined in any way. And the transfer function is practically looking at the circuit itself in terms of the what is the output and what is the input and the ratio of that, or kind of the translation of that if you want, or the transfer of that. While kind of you can call it not essentially a black box, but a kind of a black box where you don't care about whatever else is there by just looking at the input and the output. So again, it characterizes a circuit's behavior in the S domain without worrying about what else is there. And one more important thing, whenever we are doing transfer functions, we kind of make this good assumption, making our life easier, that all the initial conditions are zero. And then again, as I said, that your circuit could have multiple sources, right? Multiple voltage sources or current sources. And multiple independent sources. So any of them could satisfy your input requirement. And you can find, by the way, you can find multiple transfer functions from each of those inputs, as we have done in one of the example problems today as well, where we apply the superposition principle by looking at the output V and looking at one of these current sources, right? So at the end of the day, you can also add the transfer functions by superposition principle as well. So here's a definition for transfer function. We write transfer function as h of s, which is a ratio of y of s and x of s. X of s is the input in the estimate, and y of s is the output in the estimate, right? So again, y of s is a Laplace transform of the output signal, and x of s is a Laplace transform of the input signal. So what I'm going to do is we are going to consider a circuit here. So for example, here's a circuit. It's a series RLC circuit where you have a resistor, inductor, and a capacitor, and it is connected to a voltage independent source VG. This is a representation of the time domain circuit in S domain. So let's find a transfer function over here. Again, you can define any input and any output. For example, over here, let's say this is my input. Since I just have one independent source, so making this as an input is kind of a fairly reasonable idea, right? So my input is v of g, and then I can define my output anything over here, right? So and I'm going to find the two different transfer functions by first considering the output to be this current and then considering the output to be this voltage. Okay, so let's see. So your transfer function h of s is y of s, y of s. Let's define y of s. Why did I write this? Y of s over x of s. So y of s is the current over here, which is I, and x of s is the input Vg. Now if I look over here, right, and this is a series circuit, and your Ohm's law is directly transferable from the time domain to the S domain. So essentially you have V is equals to I R, right, or I over V is equals to 1 over R. So practically you should get 1 over Z equivalent. So 1 over R plus SL plus 1 over SC, right? So you're going to get, once you're going to solve it, you're going to get SC over R plus SL plus 1. While multiplying it by SC. Sorry, SCR, and this is going to be SCR, and SL should be multiplied by this, so it should be C and S square, right, plus 1. Okay. Right, so essentially how you solve this thing, again, you ended up taking this whole thing in the denominator and then moving S over C up by taking the whole thing into the denominator, so it gets multiplied to all the terms, right? So SCR plus 1 over SC, I can simplify. Okay, for example, S square LC plus SCR plus 1. Just writing the square term first and then, okay. So this is how this expression, I think I found it correctly. Yeah, right? So here's the expression. Again, you find a transfer function based on one of the inputs. Over here, our input is this independent voltage source, VG, and any of the outputs, we could have find the output across SL as well, right? But in this particular example, we were interested in current as being an output. So let's do one more example where we are gonna do consider voltage as an output, right? But I have like a couple of other, okay. I already mentioned that, right? So this was the output and VG was the input. Okay, here's the second example. Now let's consider the capacitor voltage is the output of the signal, right? So this voltage V is the output of a signal. Okay, so now if I were to do this, then again my H of S is Y of S divided by X of S. Y of S is capital V, X of S is VG, right? Again, I can find it, this Y of S is the voltage across a capacitor, right? So it will be I times ZC divided by I times R plus ZC plus ZL. So I will be cancelled out, 1 over SC over R plus S L plus 1 over SC. Okay, so once you can take 1 over SC common out, right? 1 over SC over 1 over SC times SCR plus S squared LC plus 1. So this will be cancelled out and you're going to be left with 1 over S squared LC plus SCR plus 1. So this is how you can find this transfer function H of S, which is V over this. Again, your transfer function is the response of a circuit to a particular input and an output. And we can define an output in different ways. Over here, we define the output across a capacitor. And this is going to be very, very useful because we're going to build some filter circuits as well in the next chapter. Okay, great. Again, this is a point that I make. If you have multiple sources, your definition of the output signal can vary as well. And you can apply superposition principle to find the total response. If you are practically, you can get multiple transfer functions, right? And then apply a superposition principle as well. Okay, let's do one example problem. So consider the circuit. It's kind of a very simple example problem where input is VG, so this drives it, and I need to find a transfer function, and the output signal is the voltage across the capacitor V0. So practically, I need to find capital, in the S domain, I need to find the ratio of V0, the capital V0 or V0 of S, right? I need to find the ratio of V0 of S over VG of S. And then whatever the expression of the transfer function is going to come out to be, I have to find the poles and the zeros of the transfer function as well, right? So if I do all the kind of the steps that I don't need to do those steps, but right, there is no initial conditions. I don't need to worry about initial conditions. And then in step number 2, we usually convert this small VG time domain Laplace transformed can be written as capital VG of S. Similarly, this small V0 of t Laplace transformed can be written as V0 of S. Right, in the step number 4, since there are no initial conditions, so my capacitor and inductor would transform into S domain by just very simple impedances, right? So before I make a circuit, let me find ZL is S times L, which comes out to be 50 millihenries, 0.05 0.05 S ohms, and ZC comes out to be 1 over SC. Capacitance is 1 microfarad, right? So 10 to the minus 6, 10 to the 6 over S ohms. Okay, this is interesting. Now I can easily draw my circuit in the S domain. My circuit in the S domain is going to look something like this, this, and a capacitor, and this, right? Again, this is capital V naught over S. This is capital VG over S, VG of S. This is 1000 ohms, 250 ohms. Capacitor replaced by the impedance of the capacitance, 10 to the 6 over S ohms, and the inductance is 0.05 S. So once you find this, and this is also units ohms, right? So I ended up finding the circuit over here in the S domain, right? Now let me find the transfer function. Before I find the transfer function, I'm going to consider, for example, this node, right? Let's call it node A. I'm going to write the node voltage equations here, right, to solve the circuit. So, and of course, the node voltage should be V naught. So I can write V naught minus VG over 1000 plus V naught over 250 plus 0.05 S plus V naught over 10 to the 6 divided by S, so S will be multiplied in the numerator, right? Okay, so if you were to solve this, right, once you're going to solve this, you're going to get the value of the V naught as 1000 S times, 1000 S plus 5000, S plus 5000 VG over S squared plus 6000 S plus 25 times 10 to the 6. Okay, so this is the expression of the V naught that you get. And of course, you have V naught over here. This is your V naught, this is your VG. Take VG on the other side, and you can find the ratio of V naught over VG and rewrite the expression, right? So the transfer function is V naught over S over VG over S should come out to be 1000 S plus 5000 over S square plus 6000 S plus 25 into 10 to the raised to power 6. Okay, so here's the transfer function. The A part asks for the transfer function. Let's find the B part. The B part asked for to find the values of the poles and the zeros. Okay, cool. Poles and the zeros are simple. Let's find the zeros. Again, zeros are the roots of the numerator, and I just have S plus 5000, right? So the 0 is going to come out to be S equals to minus 5000. This is one of the zeros. Let's find the poles. Poles are the roots of S in denominator. And again, you have a quadratic expression, S plus 6000 S plus 25 times 10 to the 6. Find the roots of this. The roots are going to come out to be minus 3000 plus minus j 4000. So you got two poles, pole 1 and pole 2. First pole is at minus 3000 plus j 4000. Second one is at minus 3000 minus j 4000. Again, these are the roots of this denominator, which is over here, of the transfer function. Again, very simple to calculate transfer functions. You have already learned enough Laplace transform, right, to solve for this thing. So transfer function is not kind of it's a new concept, but you are practically solving the same circuits. Converting the time domain circuit into an S domain, we have done that enough times. And then just writing an equation in a way that uh, uh, you are defining a particular output with a ratio of a particular input, it becomes a transfer function. Cool. And then rest of the whole analysis is pretty much the same. We're going to do one more concept in this lecture, and then we are done. And with that concept, we're also going to do an example problem. Okay, so with that, thank you so much. Have a great rest of the day.